So the first thing I'm going to explain is why a polar molecule will dissolve in a polar liquid, and it's pretty simple. Basically, polar molecules have a charge. That's the point. So what happens is in a polar liquid, the molecules also have a charge. Like the example I used is water, because everyone knows about water and its molecular structure. So the positive ions of water are going to attract the negative side of the polar molecule, and the negative parts are going to attract the positive side, pulling the molecule apart, which makes it dissolve faster and easily into a polar liquid. Whereas,
okay, so for nonpolar solvents and solutes, they both have no charge, so therefore they mix equally. So as we read in the text last night, there's this rule called like dissolves like. So polar molecules are dissolved in polar solvents, while nonpolar solutes are dissolved in nonpolar solvents. So like a real life example is like if you had grease on your hand, which is nonpolar, and you try to wash it off with water, it wouldn't come off because water is polar. So if you use like turpentine, which is nonpolar, it would come off.
and an example of a polar solution that everyone knows is all over the world is salt water.
So for our demonstration, we have in these two separating beakers, we have carbon tetrachloride on the bottom and water on the top because they've got different densities. So that's here. And then we're going to put in potassium permanganate, which is a polar molecule. And we also have iodine, which is nonpolar. And so the polar will dissolve in the polar water, and the nonpolar will dissolve in the nonpolar carbon tetrachloride. So the first is potassium permanganate. Into the separating beaker. And so you can see that it's only dissolving in the water that's on top, because the water is polar and so is the potassium permanganate. So it dissolves there, but not in the nonpolar carbon tetrachloride. Whereas the iodine going into the same setup of water and carbon tetrachloride, goes straight to the bottom and only dissolves in the carbon tetrachloride, turning it purple.
Okay, take it away.
Okay,
Thank you.
So in this beaker we have deionized water, and we use universal indicator to show that it's completely neutral because it's green. So what we're going to do is we've attached a rubber tubing right here, and we're going to put that in the water. And we're going to take HCl and put it in here. And then we also have solid or powdered calcium carbonate, which we are going to put in here. And as soon as we put the calcium carbonate in, we're going to put a rubber stopper on top to trap all the gas. So you take like a good scoopful. And try not to spill. And go. And then she will hold that, and then it's bubbling. And it's changing color. We have a lovely color change going on. So the product that's coming out of the tube is carbon dioxide gas. So it's going into the water, changing its color. And then what we're going to do is put it on the hot plate to see what happens when you increase the temperature. And this will take a little bit of time. So we'll come back. We're going to come back to that.
Okay. Sure, I'll try to explain this. Alright, so when we take the carbon dioxide from this reaction here and put it into the water, you're dissolving a gas into a liquid. So that means the enthalpy change will be negative because I guess it's like you need it's like releasing energy to turn it from a gas into a liquid, so it's a negative enthalpy change. And then the disorderliness is less, so it's more orderly because it's a liquid instead of a gas. So that'll be negative. So you have two negatives here, and you need to have a low temperature to make it a spontaneous reaction.
And that's because gas is more soluble at a lower temperature. So we know that at a low temperature, the gas particles are going to stay, like, are going to dissolve into the liquid. But what happens when you increase the temperature? We don't know. So we will see that when that's done.
Okay, and then, just to like give you an example of something that happens in everyday life, if you think about like fish in water and how they need oxygen, well, if you have factories that put all their stuff into the water, the oxygen, well, okay, so like raises the temperature, which makes the oxygen less soluble, so the oxygen will start to leave the water, and then that's not good for the fish. Just an example. Okay.
Okay, so we just talked about the gas dissolving the liquid. Now we can also talk about the solid dissolving into this solid dissolving the liquid, which is sort of a different direction
This is
for
our
the phase.
first reaction.
Yeah, so what happens here is it's a positive enthalpy change because going from a solid to a liquid requires more energy. So it's going to absorb energy and change from the solid to the liquid. And then it's more disorderly because liquids are technically more disorderly than solids because they're less contained, I guess. So two positives, it's going to require a high temperature, or at a higher temperature it's more likely to dissolve. So,
Great. Thank you very much.
So we put the CO2 gas in there once the gas was released because we raised the temperature, and it's no longer soluble within the liquid, so it's released. So then the universal indicator shows us that the pH is back to neutral because it is no longer more acidic.